Hi everyone and welcome to lesson 16. In this lesson we're going to look more into what we studied in the previous lesson where we learned about equilibrium. And so we're going to model equilibrium here. And so the learning objective for this lesson is to apply the equilibrium model to objects for which the net force is zero. So we already started to see that bit in the previous lesson, and we'll get into some more detail with it here. So recall we said that when a net force was zero, we were in we called it a mechanical equilibrium. Okay, and this of course came from Newton's second law of motion: force equals mass times acceleration. And so when we were in mechanical equilibrium, there were two types. There was one where we were at rest and one we were moving at a constant velocity. And so when we're at rest, we call this static equilibrium. And when we're moving at a constant velocity, we call this dynamic equilibrium. All right, so either which way, we had a net force of zero because there was no acceleration, right? So force is dependent on mass, so we always gonna have mass, and also acceleration. Well, we're at rest, we're not moving at all, so there's no acceleration. And if we're moving at a constant velocity, well, the definition of acceleration is that we're moving at, or we're changing our velocity. So in either situation, we have a net force of zero. And so recall that when what is a net force? Another way to say it is the sum of all the forces acting on an object. And so we also called it, we use that Greek letter sigma for sum. Okay, so and the sum of all the forces, maybe there's n amount of forces, so it would just be, well, whatever, how many forces there are, just adding them up. Okay, so in the equilibrium model, we're basically just looking at situations where the net force is zero, which means that either an object's at rest or it's moving at a constant velocity. So either one of those situations is considered equilibrium. All right, so, and if you think about it too, it's not just Newton's second law, but it's also Newton's first law, because recall that Newton's first law, the law of inertia, says that an object at rest continues to stay at rest. Yeah, that's our static equilibrium, is that part. And an object in motion will continue in that motion at a constant velocity in a straight line. So that's the second part, is the dynamic equilibrium. Okay, so the sum of the forces, the net forces, is all just the sum of all the forces acting on an object. But technically, it's the vector sum. So if we're dealing with one dimension, that's easy. We just add up all the forces, and if forces are just going in one direction, well, then we just simply add them up. But if they're going in opposite directions, well, adding vectorially would mean that one direction would have to be positive and one would be negative. Okay? And then if we have two dimensions, well, there's a simple thing that we can do. All we really say is that we just break up the x and y components. So we would say there's a net force in the x direction, which is the sum of all, that's a bad sum of all the forces in the x direction. So it'll be the x component of force 1, the x component of force 2, however many forces. So we just add up all those x components. And for the equilibrium model, we know that all of them, all the components have to add up to zero. And then the same thing for the y components. We would just add up everything in the y, all the components along the y-axis. And we know in equilibrium they have to all add up to zero. that's essentially most of the new stuff for this lesson. So most of the rest of the lesson, we're going to apply this and practice seeing what this means, what this actually looks like. So to do that, I kind of came up with these steps. I think they're really good to think about as you're solving these type of problems. What steps you should go through if you're starting to feel like you're getting lost, right? And you don't have to follow these, but if you find them helpful, then go ahead. Well, the first thing I would say to do always is to, if you're not given a sketch, draw a sketch, just a simple diagram, and then turn that into a free body diagram, right, where we identify the forces. Then find your x components, the net force, so all the sum of all the x components, find all the sum of all the y components. And then once you get to that point, try to simplify things. How can you simplify what you found out? And then the rest of the steps are sort of asking yourself questions that'll kind of cover all your bases. So I like to start off by saying, what do I know? What don't I know? What are the unknowns? And what am I able to figure out? And then always, like we learned about hidden assumptions, try to identify any hidden information there might be. And then, of course, well, what do we want to know? What is the question asking us? So in the next few problems, I'm going to go through these steps and apply them so you can see what this actually looks like. All right, so in here we have a question. We have 3 ropes that are tied to a very light ring. So we have rope 1, 2, 3, and then a ring in the middle. 2 of these ropes are anchored to walls at right angles with the tension showed. So this rope 1's anchored to the wall on the left here. Rope 2 is anchored to the ceiling, I guess. And so we want to know, what are the magnitude and direction of the tension in the 3rd rope. So we are able to figure that out with the information given. All right, so in the steps I gave you, I said, well, let's make a sketch, unless one was given to us. Well, one was given to us. So the second step then we could skip to would be to create the free body diagram. So I put a coordinate plane here, so we could set up our free body diagram on that coordinate plane. And now we can turn, we can put all the forces that are happening here. And so all of these forces are tension. We're dealing with ropes pulling. They're tied to a wall, and then there's a tension is pulling on that 3rd rope, but everything's at rest. Okay, so we're all in an equilibrium, static equilibrium in particular. And so to simplify things a little more, like we like to do, we could treat the ring. We could apply the particle model to it. We could just pretend that it's just a dot there, so we don't have to worry about all the complexity of the 2 3-dimensional existence of the ring. We can just pretend like it's just a point. All right, so let's. Oh, and another thing is, to kind of make things simple, we're going to start doing this too. We've been applying the particle model a lot, but another model we use is we sometimes, and you'll see this sometimes in questions, is that we treat certain objects as ideal, which means that there's no, we pretend like it's massless. It doesn't have any mass. If it's really light in comparison to everything else that's going on, then that works. Another way we could think of it in an ideal situation is there's no friction. So that'll just help us simplify things a bit more. So for this situation, let's pretend that it doesn't have enough mass to make a difference. Right? So we're in equilibrium. Okay, so that means that the net force is 0. and it's a static equilibrium. We're at rest. And so the next step was to find the components. Oh, and I totally skipped the part where we make the free body diagram. So let me make a, let me identify all the tensions here. So let's say we have tension 1 is that rope there. So I'm going to draw an arrow to represent that tension. So it's pretty nice. It's right there along the x-axis. So that's T1, 50 newtons. And so we could see by putting this on a free body diagram on a coordinate plane, we're really starting to see what it's really going to help us identify what forces we're going to be considering positive and negative, and whether they're along the x direction or the y direction. And let me also put right there at the origin a little dot, a little particle to represent our ring. Okay, and then tension 2 is going to be nicely along the positive y-axis. That's T2. And then T3 is going to be somewhere in between somewhere in the 4th quadrant. Okay. And so now that's basically all of our forces that are happening. And so if we think about our coordinate plane, the positive x-axis is over here, the positive y-axis is going up, right? So we can really even start to say more specifically, give some signs and directions to each force. So T1 we know is 50 newtons, but since it's along that negative, pointing in the negative x direction, we could say it's negative 50 newtons, right? Now we no longer just have a magnitude, how much tension there is, but we also know which direction, okay? And T2, since it's in the positive y-axis, that would just be positive 80 newtons. Okay. And so T1 and T2 are pretty easy. They're perfectly along the x-axis and the y-axis, but T3 we see is somewhere in between. So that means we're going to need to break it up into its components. So I'm going to make an x component, T3. There we go. And then I'll make a y component of T3. Okay, so I'll call the components along the x-axis, I'll call it T3x. So that's the x component of tension 3. And then this would be T3y, all right? The y component, tension 3. And of course, there's going to be some angle, right, with respect to the x or y axis. Okay, so now I've identified, and we could even say T1 and T2, right? T1, since it's all in the x direction, we could call that and say it's actually T1x, right? Because it's all in the x direction. Whereas T1y, really, there's no component in the y direction, so that would be 0. But we don't really have to write that down. And then T2, that's technically T2y. It only has a y component. All right, so that's our step on the free body diagram. So we've made a free body diagram. We found out, broken up everything into its components as best we can. And so then the next step is, oops. Check out the steps here. Where did I put that? Okay, so the next step I said is after drawing the free body diagram, let's find the x components, the net force in the x direction, and then the net force in the y direction. Okay, so the net force in x direction, we know that'll be 0 since we're in equilibrium. And so what is that? So what are all of the forces along the x-axis? Well, we know there's T1, okay, and T3x. Okay, that's it. Just those two are the only two components we have on the x-axis. Okay, and since we know what T1 is, we know it's negative 50 newtons. We don't know what T3x is, but we know they add up to 0. They have to add up to 0. Okay, and then the net force in the y direction will also be 0. And so what are those? Well, we have T2 and T3y. And what I'll do for T3y is I'm going to put minus T3y, because T2 is in the positive y direction, T3y is in the negative y direction. And we know what T2 is. It's 80 newtons minus T3y. Okay, so now we found our x and y components, the net forces in the x direction, the net force in the y direction. Okay, now the next step was to simplify. So can we simplify these two here? Yeah, so we could just do a little rearranging. We could say that, so let's do this here, make it a little easier, neater. Down. Okay, so if we look at what do we have here for the x direction, well, we can simplify this a bit. We can essentially say it's T3x equals minus 50 newtons. Okay, just rearrange it a little, make it a little bit cleaner to look at and think about. And then we could do the same thing with the y. We could say that T3y is equal to 80 newtons. All right. Okay. And what else do we know? Well, we also know that we know what T3x and T3y are, because we know the x components. All right, if we're looking at T3x, we can actually figure out what that is in breaking down vector T3 into its components. Well, we know that the cosine of the angle is equal to the adjacent over the hypotenuse. So that would mean T3x is going to be T3 cosine theta. Okay. And so then T3y would be T3 sine theta. Okay, so we've done some simplification now. We got about all the detail and simplified as we can. So now we can ask ourselves some questions. Well, what do we know? Okay, what can we what are we what don't we know? What can we figure out? Okay, so we kind of already knew we kind of already jumped ahead with that because we knew what T1 was. We knew it was the negative 50 newtons, so we already put that in. We knew that T2 was the 80 newtons, so we've already put that in. So what don't we know? Well, we don't know what T3 is, and we don't know what theta is. So I'm going to put that down here. T3 question mark and theta equals question mark. Okay, and you can jump around with the questions too, because sometimes after this point we might say, well, this is what we know, this is what we don't know, but it might be a little harder to say what can we figure out or what hidden information is there. Okay, so you don't have to do these questions in the exact order, but these are just questions to help guide you. And you can go, check back and forth with them as you do the problems. So we might say, well, what do we want to know? Well, the question was, what's the magnitude and direction of the tension in the third row? Okay, well, that's what our two question marks were that we said, well, we don't know what these things are. Okay, so that's what we're looking for. So, oops. So I'm just gonna box off these two statements that we created. Okay, we created, developed these two equations to represent what's going on with the net force and horizontally and vertically. So those are going to be important to us. So what can we figure out what T3 is? Can we figure out what the angle is? Okay. Well, sometimes we can substitute one equation into another, but can we actually do that? Here? Well, yeah, maybe we can. So let's give that a try. So if we solve for T3, okay, or let's see. So one of them we could solve for T3, and then possibly insert it into the other one. So let's say the top one would be T3 would be negative 50 newtons over cosine of the angle. Okay, and then we can insert that into the second one. So then we would have something like negative 50 newtons over cosine theta times sine theta equals 80 newtons. Okay, so we got rid of the T3, but now we also have a sine theta and a cosine theta. So, so are we stuck? Can we go any further? Well, this is where it might be useful to go back to say, okay, what can we figure out? Is there anything else we could figure out? Is there any hidden things that are known that we really just kind of didn't notice? Okay, and so maybe some of you noticed this, but it might also be something that many of you have forgotten from trigonometry, but there's a special relationship between the sine of the angle and the cosine, right? Sine divided by cosine is actually the tangent function. Okay? And so now
say, oops, 80 newtons over minus 50 newtons. Units cancel. And so the theta, the angle, is actually the inverse tangent of 80 over negative 50. And I got about 58 degrees. Okay, and actually that comes out to negative 58 degrees, and so that makes sense. We're 58 degrees below the positive x axis, so so we're good there. So now we found the magnitude, or not the magnitude, the direction. Now we can find the magnitude, can't we? Okay, well, we know we can use, now that we know the angle, we can use either relationship to determine what the magnitude is. So I'll go ahead and use the second one, doesn't really matter. And here, so we have T3 sine theta equals 80 newtons. So T3 will be 80 newtons divided by sine of, what is it, minus 58 degrees. Okay, and here I get 94 newtons. Okay. Right, and so the negative really wasn't necessary there, but because we're just dealing with the magnitude, right? Magnitude, we don't have direction. We already figured out what the direction was, and really we didn't even need to know that this was negative here because we knew that we were solving for this angle here. Okay, so we really had already set it up, so we knew where it was going to be. It was going to be below the x-axis, but the negative there helped a little bit. Okay, and so as you practice this, it'll go by quicker and quicker. It won't necessarily take so much time. All right, so let's try another one here. So this time, now we have a loudspeaker, 20-kilogram loudspeaker. It's suspended 2 meters below the ceiling by 2 3-meter long cables. They're angled outward at equal angles. And what is the tension in the cables? So here we're not given a diagram sketch. So it'd be good to make one, try to visualize what this situation is. And so we know we have a loudspeaker suspended from a ceiling. Okay, so first thing I'm going to do is I'm just going to make a ceiling here, just a flat line for our ceiling. And we know that we have a loudspeaker that's being suspended from it. So just draw a little box to represent the speaker. And it's being suspended by two cables that are angled outward at equal angles. Okay, so they're angled outward. So that's going to look like this. All right, so something like that. And we know that they're 3 meters long, each one of them. And what else do we know? Well, we also know it's suspended 2 meters below the ceiling. So this straight line distance down the middle, that's 2 meters. Okay. So that's about all the information we can really gather. But now we have kind of a nice visual of what's happening here. And so the next step is to go ahead and turn this into a free body diagram. So again, with the free body diagram, I'll go and represent the box as just a point, okay? And what are the forces going on here? Okay, well, we know that we have a tension from, so maybe this is T1, and another tension T2, okay. And theoretically they're equal, right? Because what are we told? That they are both the same length and they're angled outward at equal angles. So those tensions are actually going to be the same. And what other forces do we have going on here? Well, now that we actually have an object that has mass, right? We can't ignore the 20 kilograms. Well, now we have the force due to gravity, and that always points straight downward. All right. Okay, so are we in equilibrium? Yes, the speaker's hanging there, and we're in a static equilibrium, right? It's not moving, it's at rest. So now our next step was, let's go ahead and find the components. So, well, when we look at this, we see that, well, gravity is only along the y-axis, so that's easy. But T1 and T2 are going to have both x and y components. Okay, so let's break those up and have a x component, of T1. So we call it maybe T1x, an x component of T2, call it T2x. Okay, and then we'll have a y component of each one. I'll call this purple one T1y. And then maybe I'll make a red one just to distinguish that there's two of them. That one be T2y. So that when we're making this free body diagram, we can actually see that there's two components there. Okay. So now we can find what is the net force in each on each axis. So the x-axis, the net force in the x direction. We know it's at rest, it's going to add up to 0. And what do we have? Well, we just have the components of x component of T1 and T2. So the x component of T1 will have positive since it's moving in the positive, or it's pointing in the positive x direction. And then I'll make T2x, I'll make that negative. Okay. And if we wanted to go ahead and put it in right now, we could put in what would be what would that actually be breaking it into its component? Well, T1x would be T1 cosine theta, and T2x would be T2 cosine theta. Okay, now what about the net force, the y component of the net force? All right, well, what do we have? Well, now we have a few things. Well, we have two components in the positive y axis and one component in the negative. So we can go ahead and say T1y plus T1 or T2y minus FG. Okay, that's our total there. And we could also simplify a bit more. We know that T1y is going to be T1 sine theta. And T2y will be T2 sine theta plus force of gravity. Okay, and then we can go ahead and simplify this a bit more. We say that for the x, well, these two here are equal to 0, right? So then to simplify that more, we could basically say that T1 cosine theta equals T2 cosine theta. Okay, and then for y, we could say, let's see here. Oh, I actually made a mistake down here. I did plus force due to gravity. It should have been minus. So we could simplify this. We could say T1 sine theta plus T2 sine theta equals the force due to gravity. Okay, so I think we got everything about as simplified as we can get it. So what do we know? What can we figure out? Well, we know that the mass is 20 kilograms. So that means for the force of gravity, we can actually figure that out. That's mass times gravity. So 20 kilograms times 9.8 meters per second squared. Okay, and that'll give us 196 newtons. Okay. Let's see, what else do we know? We knew that we had a length here of 2 meters, a length here of 3 meters. And I guess that's about it. Okay. So, any hidden unknowns? Well, I think I started to allude to it before, but remember that since T1 and T2, they're angled at equal angles, well, their magnitudes are going to be the same, right? Okay, so so T1 is actually, we could say, is equal to T2. Okay, I'll just do that in a different color here. T1 equals T2. So that might actually help us in some way if we keep that in mind. And so that also means that our angle here and our angle here has to be the same. Okay, perhaps that will help us. And we can actually figure out what that angle is. Because if we look at our free body diagram or our sketch that we made, okay, we can sort of make another x-axis here. Okay, so we have another. We can make that an x-axis because that's parallel to the ceiling. Everything's just kind of hanging there straight. Everything's balanced, and this angle here is the same as this angle here, right? And this angle here, and this angle here. And so can we actually figure out that angle? Well, what do we have here? We have a hypotenuse here, and we also know the distance below the ceiling is 2 meters. So this would actually form, we can move that over here, right? And make a right triangle. So we got a 2 meter one side, 3 meter on the other. We can figure out what the angle is, right? Because if we do the sine of the angle, it's the opposite over hypotenuse. So 2 meters over 3 meters. And so 2/3 sine, oops, no, inverse sine. And I get 41.8 degrees. Okay. So now we have an angle, okay, um, of what that angle is. Okay, so that should help us. So now what are we looking for? Well, we want to know what is the tension in the cables. Well, we said T1 and T2 are going to be the same, so if we figure out what one of them are, then we know what's the other one is. And so let's see, what do we have here? We have, let's see, well, this, oops. So this one has both T1 and T2 in it. If we substitute, if we also call that T1, does that really help us? No, because we know obviously T1 cosine theta is T1 cosine theta. So maybe we can figure it out from this one. Okay, so we could say here now that, all right, that's T1 sine theta plus, well, T2 is also T1, so we can call that T1 sine theta equals force of gravity. And then basically we have 2 T1 sine theta equals force of gravity. And so solving for T1, we get force of gravity over 2 sine theta. And we had already figured out the force of gravity is 196 newtons. And 2 times the sine of the angle, let's see, sine 2 divided by, and I get 147. 147 newtons. Okay, so that means T1 is 147 newtons. That also means T2 is 147 newtons. Okay, so that one went a little bit quicker. And this is also something that's sort of useful because this has some applications to engineering or even simple things that you can do at home if you're hanging something, if you're hanging a speaker or something, and if it's something that can't handle a lot of tension, or maybe the thing you're trying to hang it with is not very strong, well, you could change the angle or add more ropes, and that will help you help you to hang something a little bit easier and safer. Okay, and always make sure, of course, to hang it in a stud in the wall, not the drywall. Okay. Okay. So let's look at one more example of this. And so now here we have a car with a weight of 15,000 newtons being towed up a 20-degree slope with a constant velocity. Friction is negligible. And the tow rope can withstand a maximum tension, spelled tension wrong, of 6,000 newtons. Will the tow rope break? So we're not given a sketch here or diagram, picture or anything. So let's go ahead and make one. And so we have a car is being towed up a 20-degree slope. So I'm going to make a 20-degree slope here. And what I'll do here is to indicate it's 20 degrees, I'll make a dotted line for sort of a flat surface. And so that's 20 degrees. And then we have some sort of car or something being towed up the slope. Okay, and so maybe this is the tow rope going up the slope. Okay, so we have a little sketch here of what's going on, and so we can go ahead and make our free body diagram, and you also notice that I kind of already tilted the axis here on our coordinate plane in anticipation of doing this. And so now we can call that slope that's on a 20-degree slope, that hill or whatever it is. We can refer to that as our x-axis. And so let's go ahead and represent the car just with a point, a dot or something, a particle. And what kind of forces do we have going on? Well, we know tension is pulling it up along that x-axis, that tilted x-axis. We know that it's on a surface, which indicates that there's going to be a normal force perpendicular to the surface. And there's also, it's a 15,000 Newton weight, so that means the force of gravity points straight downward. Okay, so those are all of our forces going on. So we could say, kind of to help us picture this a little bit better, I'll also make our flat surface there, and indicate our 20 degrees here. And so what else do we have? Well, we know that there's going to be some components here. We have tension is perfectly along the x-axis, and the normal force is perfectly along the y-axis, but now gravity, since we tilted the axes, and gravity always points straight downward, but we tilted the axes, now it's partially in our defined positive or x and y coordinates. So we're going to have mark out the components of that. So we'll have a x component of force due to gravity, and we'll have a y component. Right, and then also, if you recall from an earlier lesson, this angle here is also 20 degrees. All right, so we made our sketch, we made our free body diagram. Well, we know that we're in equilibrium, right? This is actually dynamic equilibrium this time, because we're not at rest, but we are moving at a constant velocity. But it still means that the net force is 0. And so we can find what are the x and y components of the net force. Okay, so for x, we know it's going to add up to 0. And for x, we have, I didn't label it here, that's tension. Tension is positive, and x component of gravity is negative. And we can rearrange that to be tension equals the x component of the force of gravity. And then for the y, also is going to equal 0. We have the normal force, which is positive, minus the y component of the force due to gravity. And simplifying that, we can say normal force is equal to the y component of the force of gravity. All right, so let's see here. What are the unknowns? Well, we know the weight, right? So the full Fg we know is that 15,000 newtons we were given, and we are not really given anything else except for the fact that we have a slope of 20 degrees. We're moving with constant velocity, and we want to know if the tension is basically less than the 6,000 newtons.
So we want to find out what is tension. Okay, so we saw that tension is the x component of the force due to gravity. Okay, so let's see if we could figure that out from that. Well, so tension, x component of the force due to gravity is Fg cosine of the angle. Okay, so what does that actually look like? The x component of the force of gravity. It's like this here, but how can we figure that out? Well, remember that we could bring this parallel line. We can also bring it down here. Okay, so what I'll do is I'll draw a parallel line going here. That's parallel. And what have we done? Well, now we've made a right triangle here. And so the sine of this angle, or the cosine of this angle, no, it actually, yeah. So in this case, it's so typically the adjacent is cosine, right? But we're actually for here, it's not the this is not adjacent. This is actually opposite here. Okay. So if we want to find this side, which is parallel to this side, which would be the x component of the force of gravity, will be the sine of this angle, this opposite over hypotenuse. Okay, so it's not going to be cosine theta here. It's going to be Fg sine theta. Okay, and we know that the Fg, the weight, is the 15,000 newtons. And we know the angle is 20 degrees. Okay, and so if we do that out, we get tension of 5,130 newtons. And we wanted to know, what's the question, will the tow rope break? Well, it can withstand a maximum tension of 6,000 newtons. Well, the tension that's actually in the rope is 5,130 newtons. So yeah, it's getting close, but it shouldn't break, right? It's less than that 6,000 newtons. Okay, now, so for the final part of this lesson, we've started really getting into the force due to gravity. We've been saying that it's the mass times gravity, but what's really the difference between mass and weight? Okay, or this force due to gravity. Well, what is mass? Well, you probably maybe have learned, I'm sure, in chemistry and maybe some other courses, what is mass? Well, it's a property of matter, or sometimes we describe it as the amount of matter in an object. And we also use it as description of an object's inertia. So if you have a large, heavy object, like a train, it has a lot of mass, which means it has a lot of inertia. So that means it's really hard to get it to stop moving, right? That's Newton's first law, the law of inertia, is that an object in motion wants to continue to stay in motion in a straight line at a constant speed. Well, we really see that. The more inertia something has, like a train, then it takes wants to keep moving in that. So more matter, more inertia, more harder it is to stop. And whereas weight is not the same as mass. It is a measurement. So what are some of the units of mass? Well, we know that the SI unit is the kilogram, and maybe sometimes we use grams. Weight, well, weight in SI units is the Newton. We often here in the US use pounds, right? If we want to talk about the weight of something, how much do I weigh? But to say maybe you weigh 50 kilograms, that's not accurate.
because kilograms is a unit of mass, not weight. So it's completely inaccurate to say that you weigh a certain amount of kilograms. You have a certain amount of mass of kilograms. And so, but weight has to do um, with the measurement, okay? And that really has to do with gravity. So we've been seeing that the force due to gravity, right, is weight, object's weight, and we've been doing mass times gravity. Okay? And so if we want to find out what an object's weight is, we might say W for weight is mass times gravity. But this is actually the same as saying weight is a force, a measurement of force. Weight is really can also be described as Fg, and g is just a type of acceleration, right? And so really by doing this, we see that to find weight, we're really just talking about Newton's second law of motion, that force is mass times acceleration. Okay, so we see in a bathroom scale, traditionally there's some springs that get compressed in the scale, and when you step on the scale, what happens is gravity's pulling you downward, and the springs are trying to push you upward. Right, we get this normal force happening, and sometimes you'll see on the scale, especially older ones where there was a dial, would kind of wiggle back and forth until it came to rest, just because of that, the bouncing from getting onto the scale. Then it would finally reach an equilibrium. It would be no longer back and forth, and so there was a net force there of 0. Okay, so when you're on the scale and it finally balances out and gives you a reading that's not changing, well then we're in equilibrium. We're static equilibrium. We're at rest. Okay, so that upward force from the spring is perfectly balancing out that downward force due to gravity. Okay? So when we're talking about the weight of an object, right, its mass times its gravity, we're talking about the weight of the object at rest. Okay, and so we'll see in 2 more lessons what happens when we're not at rest and what's going to happen with that scale reading. So to think about the difference between mass and weights, we can consider this question about an astronaut taking her bathroom scale to the moon, where gravity is 1.6 meters per second squared, whereas on Earth it's 9.8. So it's 1/6 of what it is on Earth. So on the moon compared to at home on Earth, how does her weight and mass compare? We're going to look at those options for a moment. And so right away you should be able to see that C and D are the only reasonable choices because mass doesn't change. Mass is a property of an object. It's amount of matter in an object. So if she was identical when she left Earth to when she got on the moon, then her mass would be the same. Okay, but the correct response would be that her weight is less. It's not 0. Okay? If her weight was 0, there'd be no gravity. But we know that there's a little bit of gravity. It's much less than Earth, but it's not 0. So she would weigh less, but has the same amount of mass, unless she happened to go on a diet or something in the time and the days that it took to go to the moon. But as you know, if you ever tried dieting, you don't really lose that much in the first few days. So essentially, that's what we're considering here, is that we're assuming that she's the exact same mass as she was when she left the Earth. All right, so you should be able to do these 4 homework problems now. There's also another problem on Moodle if you want to take a look at that example, but I think we did several examples here. So, but if you need it, go ahead and look at that. And so did you learn to apply the equilibrium model to objects for which the net force is 0? So we know in equilibrium, we have, we're either at rest or at a constant velocity, but either which way, it's equilibrium. And there is a net force of 0. And we can break this up into its x and y components. And then if you want, you can follow these steps. If you're having some trouble, or if you develop your own way of doing it, that's fine too. But these are just some things that I think will help you get through the problems, especially if you get stuck. Right, and that's it for lesson 16.